Hello and welcome. This is rotational motion, part one. Rotational motion of rigid bodies. Now this topic is really similar to circular motion. But in circular motion, what we did was using point particles and observing the motion in a circle. So this could be the path of a satellite orbit, as you call, around the Earth with a given radius and tangential velocity. We saw that there would be some acceleration. Now, if it is with a constant speed, the acceleration is only radial. But if there is speeding up or slowing down, depending on which one it is, there will be also a tangential component for the acceleration. And the radial component would be equal to v squared over r. And the tangential component, like I said, depends on whether it's speeding up or slowing down. If it is speeding up, it's parallel to the velocity. If anti-parallel, that's because it's slowing down. Now, but that is for a point particle. So this was just simple circular motion. Circular motion of a point particle. What about a distribution of particles, distribution of mass? And this mass will rotate about a center. Now, this is closely related to the circular motion, but you have to be really careful because of this mass distribution. Some arbitrary shape, okay? This could be a football, or it could be a compact disc, or, you know, you're entering a building, you open the door, or there's a revolving door. I mean, the possibilities are pretty much endless. Okay, you can simply let a, this is called a physical pendulum, you know, not a ball attached to a string, free to go up and down, swing, but maybe in your book, you know, swing like this. That also is a rigid body rotation. So we're talking about distribution of mass where those particles are attached to each other. So they form a solid object, a solid body, a rigid body. So we don't really consider in this section about tornadoes, okay, or water swirl, you know, that is a different story. So let these be solid objects that we want to analyze. It could be any mass distribution around, okay, let's just arbitrary mass distribution, and you let this rotate about an axis that goes through the object, so there's a rotation. Okay, so that is what we're gonna do here to analyze the motion of this rigid body. Now, if you consider each tiny particle, each element that forms this rigid body, assume this, there's a little cube here, very tiny cube of mass m, and that is, let's say, r away from the center, okay, very small portion. Let's call this actually M1, how about that? And this is R1 away. And then maybe there's another one here, which you may call M2, and that is R2 away from the rotation axis, okay? So these R's actually are at 90 degrees with that axis. Okay, so if you just focus on those particles, yes, their motion is a circular motion, just like the one on the left, all right? So these guys will follow a circular path around the axis like this. This one has a radius R1, and this one will have a radius R2. So here's the plan then. If we understand circular motion, we'll understand what rigid body rotation is. but we have to think about the mass distribution and how these masses are distributed, and then how do we take into account these masses with a varying radii from the center. That's the main approach here. So let's start with the basics. Like, let's define our kinematics variables. In linear motion, we had position, velocity, acceleration. So we have those here as well, and some of them we already actually saw in the circular motion. Let's remember it quickly. So we had the position variable now as, we have theta as the position variable. Theta. Now this will be the angle that this radius vector will make measured from an arbitrary axis. So let's look at the top view of this picture here, top view. The top view is, again, some arbitrary shape, depending on what this original shape is. And here's your axis, right? Now the axis here comes out of the whiteboard towards you, let's say. And the rotation is counterclockwise. Okay, so here's the side view. But now we have the top view. In the top view, the rotation axis is towards you, coming out of the board. Usually this symbol is used for that. A dot and in a circle. This means coming out of the board, out of page. Okay, and then this, which is a cross inside a circle, this means into the page. Okay, so what we have here is just an axis, all right? And of course, an axis will have positive and negative directions, okay? So take your pick. I just said coming out of the page is positive, fine. But this rotation is about that axis, and you measure this angle from some other axis, which is perpendicular to the rotation axis. So let this be some arbitrary axis. And here's the point that we considered in the beginning, which was called M or M1. And here's the radius that goes with it. So the circle that it makes around that axis is this. That's our path for that tiny particle M, which is just one of the thousands of little particles that make the rigid body. But the angle theta is the angle measured from this axis. So this is the radial direction, and you measure the angle from here, theta. All right, so theta increases like that. So a second later, your object will come here. Okay, with some increment here, which you can call delta theta, all right? So delta means a difference. Final minus initial. So this was a second ago, theta initial. Now it is theta final. So here, this angle here is now theta final. So this delta theta is just the difference between the two. Delta theta F minus theta initial. Okay, it goes like this. So the angle will go from 0 to 2 pi. All right, so we measure this angle in radians, not in degrees anymore. So it's going to start at 0, or whatever it was, at t equals 0, all right? But the range goes from 0 to 2 pi for one cycle, one revolution. After that, you know, you keep adding to that. So 2 revolutions means 4 pi. Okay, 3 revolutions means 6 pi goes like that. Again, this idea of radians comes from the concept of the arc length and circumference. So I think I explained these in the circular motion videos, but let me quickly go over those. So the circumference of a circle is just 2 pi r. Let me just use the letter capital R here for any radius. But if you're talking about a portion of that circumference, which is an arc length, in this case, that will be delta theta, which is the angle that corresponds to that arc length. If you multiply it by, let's do it here, for a circle of radius r, you just multiply it by a circle of radius r, a radius which represents the circle here. That gives you an arc length, which I can name delta s. So in this picture, okay, let's use green here. It corresponds to this tiny portion here, if you can see. Okay, I'm just shading it with green there. That's the length of that arc. All right, delta s. So if you complete one cycle, that corresponds to 2 pi. If it is only a quarter of a circle, it's pi over 4, which is 90 degrees, right? And 180 degrees would be just pi. So it goes like that. So, okay, that's the way to convert degrees to radians, which you're already familiar with because you've seen circular motion before, okay? So please don't go through these videos before you watch the circular motion videos, okay? They're closely related. I'm just quickly reviewing the basic concept. So that's what theta is, all right? And from theta, we have delta theta, the difference between the final and initial, which is called the angular displacement. So the second variable here is the angular displacement, delta theta. Now, why is delta theta a better quantity to work with for kinematics? Because it doesn't depend on this arbitrary axis here, the one in red, okay? This was totally arbitrary. You know, different observers would have different measuring points, references. You're ignoring it by just taking the difference, the delta theta. It works for all axes. Now, this happens in time, so there's a time interval here, delta t. So theta I is the angle when time is ti, the beginning, and then theta f is when time is tf. So we're talking about a time interval, delta t, which is t final minus t initial, okay? And most of the time, you just start your stopwatch when theta is where you want it to be, theta I. So ti is 0 most of the time, okay? So in that case, instead of dealing with ti and tf, you just use t, the variable t. You drop the index f, and ti is 0. So this means ti was chosen to be 0. That's when you start your stopwatch, and tf simply is t. Okay, just a simpler version. Okay, so it happens in delta t. So what you do is you divide this delta theta, the angular displacement, by delta t, and that gives you the average angular velocity, which is shown with this variable omega. Okay, so omega average. This is the average angular velocity measured in radians per second. Second is a time unit. All right. So again, these were explained in the circular motion videos, maybe in more detail. So you can just watch them again, or if you remember them, just refresh your memory. With omega, what you can do is you can look at the changes in theta for very short time intervals, all right? Infinitesimal time interval. So it's taking the limit when delta t goes to 0, okay, very small infinitesimal increment in time, then this ratio will be just called omega, which means the instantaneous angular velocity. Instantaneous angular velocity. All right. So in those videos, if you watch them, there's a plot, a sample, you know, how theta will vary, and then you find the slope of the line that joins 2 points along that graph, and then take smaller and smaller time intervals. That's how we approach that limit. So this becomes the slope of the tangent to the curve at that point. So here's your theta as a function of time, some arbitrary function, right? So what you want to do is you pick a t, that's your instant, all right? Let's say this t here. And then you find the point on the curve, and then you draw a tangent to the curve. Okay, the slope of this curve is what omega is, the instantaneous angular velocity. Okay, find the slope of this. That's going to give you omega. All right, so the unit will be radians per seconds. Now, what if omega itself is changing? All right, speeding up, slowing down. So what if omega itself is changing? We're talking about a delta omega, which will be omega final minus omega initial. Same idea, we take this and then divide it by delta t. This will be called average angular acceleration. The letter alpha is used. Acceleration, average angular acceleration, and then the limiting idea applies to this as well. So limit delta t goes to 0, delta omega over delta t is simply the instantaneous angular velocity. All right, so if you've taken calculus, you'll remember that these will correspond to the time derivatives. First time derivative of theta is what omega is. Similarly, alpha turns out to be the first time derivative of omega, d omega by dt. If you've never seen calculus, don't worry about that part, but that's just the derivative. Actually, if you take this one more derivative of theta, you can write alpha as d squared theta over dt squared. Okay. All right. Now, can alpha change? Of course. Why not? It may change as a function of time. But for practical problems, we're going to assume alpha remains constant for most of the time, okay? Because we have some practical equations for kinematics which apply in that case when alpha is a constant. All right, so the next thing I want to remind you is the vector nature of these variables, all right? Now, let's go back to this picture here, the first one, the side view rotational motion. So where is the linear velocity vector for m1, let's say, okay? So if the spinning is counterclockwise, looking from a top, this means there is a velocity vector that I'm showing here with green that points this way. V, all right? And this V is perpendicular to the radius. And the radius itself is a vector. It's a position vector, right? So the radius itself is a vector. R. So if there are only two options for rotation, either clockwise or counterclockwise, okay? And if we want to find a direction for omega, all right, the direction of the rotation should be determined, whether it's clockwise or counterclockwise, determined by the direction of the angular velocity vector, okay? So let me clarify this. This linear velocity, v, is on the plane of rotation. So let me just draw a plane here. This is the plane of rotation. This plane is perpendicular to the axis we're talking about here, this axis. Okay, so the rotation happens along this circle. Okay, let me make it a bit nicer here. All right. So this is the 90 degrees that the plane of rotation makes with the vertical axis. This is the angle. This is the rotation axis. So the velocity vector have infinitely many directions, but they're all confined to the plane there. So when the object is here, for instance, yes, it is it's tangent along a tangent line. We know that, so it's pointing this way. That's v. But when that little particle is here, it's going to point in this direction. Here, this direction. It goes around the circle. Therefore, the velocity vector is always perpendicular to the position vector, right? So this is the position vector here, r, whose magnitude is the radius here. All right, but the velocity we are interested now in is omega, and the direction for omega should tell you one thing: which way is it rotating? Is it clockwise or counterclockwise? Okay. Are you entering the room while you open the door, or you're exiting the room? All right, so rotation, actually, when you enter the building, you have to open the door. When you exit, you push it. The rotation direction is the same, but you know, opening the cover of a book and then closing, okay? Now, these two correspond to different angular velocities in terms of direction. So if we have only two options, open, close, clockwise, counterclockwise, etc., this means there are only two options. And if you look at this picture that I just drew here, it's either up or down. That will be the direction for our omega. So possibility one is that omega is pointing upward. That corresponds to one type of rotation. If omega is downward, it corresponds to another one. Now, which one is which? Which one goes with which? There's this rule called the right hand rule, okay? Not the left hand, but the right hand. So you curl your fingers in the direction of rotation, like this. And then the thumb will show you which direction omega points at. So the other way around, a clockwise rotation looking from top would mean that omega is actually pointing downward. But this type of rotation means omega is up. Okay, so omega uniquely tells you which direction the rotation is. Now, V may increase or decrease, speeding up or slowing down. That won't have no effect on the direction of omega. Omega will still point in the same direction as long as the rotation is in the same direction, okay? Now, if you go back to the definition of omega now, you see there is this operation here, even with the delta theta over delta t. So for this equation to make sense, starting with the average, or even the instantaneous, doesn't matter. If omega is a vector, now I'm going to put an arrow on top of it, then you got to say, okay, it's a vector equation. Both sides should be vectors, so theta must be a vector too. All right? Now, this may not be very intuitive, all right? Thinking of the angle as a vector. Actually, it will not have any practical application in this chapter, the vector nature of theta, okay? But just for completeness, let me just show you why it is a vector or how we can define a direction for that vector. Now, in this picture here, theta will be measured from some axis. I already told you, right? So let's draw an axis here. Okay, this is the position vector. Suppose you're measuring this angle from this arbitrary axis here. So this is your theta. All right, so that black line still is on the plane, okay? I'm not sure if this one looks very good, but you know what? Let me just get rid of this one here. Maybe show it right here. Okay, so this is the angle here, theta. As a number, as radians, that's the angle. But if I want to associate a direction to theta, I'm going to pick the vector theta up, pointing up like this. All right. So the direction is upward. I have theta as a vector and omega also as a vector. Now this won't really have practical applications, really. You may think of it as, you know, maybe in terms of the right-hand rule too. If the theta is increasing this way, theta vector points up, all right? Just for completeness, I had to mention the vector nature of theta. But what is really important here is that omega is a vector, all right? And that tells you whether it's a clockwise or counterclockwise, depending on which way you're looking at, rotation. So if theta is a vector, omega is a vector, what about alpha, right? Here, omega is a vector, so is now alpha. Again, the possibilities for alpha is not that many. It's either up or down, all right? But the direction will tell you whether it is speeding up or slowing down. So without changing the direction of rotation in this example here, I still have two options for alpha. It's either pointing downward, sorry, not omega, alpha, or upward. Now, if it is parallel to omega, this means the object is speeding up. If alpha is anti-parallel, it means the object is rotation-wise slowing down. All right. So just by looking at alpha, you will never know which way the object is rotating, clockwise or counterclockwise. You have to check it with omega. It's actually omega that tells you which way it's spinning. If omega and alpha are parallel, speeding up. If omega is up but alpha is down, it's still spinning this way, only slowing down. Speeding up would mean alpha is up, but slowing down means alpha is down while omega is still upward. All right. If omega is pointing downward, then you flip those expressions in the parentheses. All right. So that's what the vector nature of these velocities tell us. Now, what about delta S? Okay, going back to this delta S here. What about delta S over delta T? What does this correspond to in this picture? Especially when I take the limit when delta T goes to 0. Now that is the instantaneous velocity v. Okay, v, but v is a vector. V is a vector, so delta S is also a vector, right? So delta S, or you can just call it S, if you will, that points in the same direction as V, all right? So in this direction, S. Okay, this is the linear displacement along the circle in a very, very short time. All right, so I'm just including this to complete the story here, because we have 3 position variables, you know, theta, r, and now s. And these are also related. So here's theta, here is r, and here is s, and these are all perpendicular to each other. Basically, r and s are on the same plane. So theta is perpendicular to r and s, and r is perpendicular to both theta and s is perpendicular to r and theta. Okay, these are just like the unit vectors along the Cartesian coordinate axes, x, y, z, or I, j, k hat, if you remember. So one of them will be obtained by taking the vector product of the other 2. So that also works. Remember, there's a right-hand rule for that too. In this case, you don't use this version, but the 3-finger version of the right-hand rule. You basically take the vector product of the thumb and the index, which will give you middle finger, or the direction that is represented by the middle finger, because the middle finger is perpendicular to both index and the thumb. Okay, go like this. Thumb cross index gives you middle. Or you can change the order. Index cross middle gives you thumb. Or the vector represented by the middle finger, cross product of that with the vector that is represented by the thumb will give you the direction of the vector, product vector, right? It's a cyclic relationship. All right, so you can apply it to I hat, j hat, and k hat. if you remember from Cartesian coordinates and the topic of vectors. Maybe you have to review that. I cross j will give you k, right? But also j cross k hat will give you I hat. And if you change the order, that would be the negative. So this is equal to negative j cross I hats. All right. So you can apply it to theta, r, and s as well. So theta cross r would give you s. Theta cross r would be equal to s. So that's how these variables are related. But as I mentioned, the vector of nature of theta will not be really used that much in our analysis from now on, okay? I just included it here. But from now on, I'm going to stop mentioning about theta being a vector and all, but omega and alpha, I'm going to be needing those two as vectors. All right. So now some part of this was already covered in circular motion. So if this one page here doesn't make too much sense, please go back and watch those videos, and there's more detail in those. One more thing, the unit for alpha will be radians per second squared. That will be radians per second squared. Now, can you measure these in terms of other units? In terms of rotation or a revolution, that's another way. So let me clear this page here and then talk about alternative units. So we have 1 revolution that corresponds to 2 pi radians, okay? So x number of radians per seconds. So some value here, but that's given in terms of radians per seconds. All you have to do to convert this to, let's say, revolutions per minute, RPM, right? Just you have to multiply this by the conversion factors. So 1 revolution is 2 pi radians. Now this radians will take care of that. We have seconds here, so how about 1 minute, which is 60 seconds. So the seconds will go. So you take this number here, multiply it by 60 and divide by 2 pi, you will have your answer in terms of RPM, revolutions per minute. Okay? The record, the vinyl record, most of the time is 33.3 or a third, let's say, RPM, a constant omega for a record, okay? For a compact disc, this will not be a constant. It will change because of the reading of the data. Okay, so if you have, this is for a vinyl record, let's say. Now this could be a single 45 or, you know, even faster, 70 something, the old ones, but this is very standard, 33 and a third for a record. Constant omega, as opposed to a compact disc. Compact disc. Now, I don't know much about technology here, but it's a laser. There's a laser here that reads the data in terms of ones and zeros. Let's say the laser starts reading from the outer section here, from the rim. If the data, which is just a collection of ones and zeros, goes around in a circle, or spiraling towards the center, let's say, okay? This is how your data is listed, okay? Maybe miles long data. You're just reading ones and zeros. 1 0 0 1 1 1. Okay. Think of it like a tape. Okay, and then along that direction, you read those numbers. So if you want to be able to read your data with a certain constant, reading speed, what you need is a constant linear speed, constant linear velocity. Okay, this is not the case when the record player. Okay, you have a turntable, and this is where you place the record. All right, so it's right here, and then you have the arm and the needle. Okay, again, you have to spiral down, spiral toward the center, but the data recorded here is the analog data. Okay, the vibrations of the needle back and forth. These are in the direction perpendicular to the direction of motion. All right, so on the on the record, there are grooves. Okay, so this, if you zoom in a record, and here's the needle. Okay, here's the needle, or what do you call it, stylus? I forget. Okay. So the vibrations of this needle, right or left. It could be right or left, or up and down. Okay, these 3D motion will be amplified, and then you'll hear it as music. But when this happens, the velocity is either coming towards you or into the page. All right. So that velocity will change. That will be changing because omega is a constant. Now that's a very important topic. For a rigid body, since the distance between 2 points, let's say a point you pick on the rim, and then over here, that's the beginning of side A and the end of the side A, right? Now, the physical distance between the two does not change. That's what makes it a rigid body. If the angular velocity is a constant, this means those 2 points you pick along that radial direction will complete the same number of rotations or degrees or radians as the rotation happens, right? So if you make one full revolution, both of these points on the rim and toward the center complete 2 pi radians. But those 2 points, would they have the same V? The answer will be no, it won't. So that's the main difference between compact disc, CD, and your vinyl record. On a compact disc, you got to have the V here as a constant. In the case of a vinyl record, omega is constant, which makes V not a constant. All right. Imagine a little bug on the record, rotating with the record, and maybe the bug is not crawling yet, but there will be a wind, okay, because of the air rotation. So that wind will have a speed, and the greatest speed will be at the rim, and towards the center, if the bug starts to walk, the wind speed will go down. At the center, the bug will just rotate around itself with 0 V. So there's a linear relationship between the velocity and how far you are from the center, all right? So V is proportional to the distance r from the center. So comparing 2 points which have the same omega, but their v's will vary depending on what r is, which makes this relationship equal to omega times r. Why? Because different speeds, let's say v1, if you divide it by r1, you get a constant, and this has to be equal to v2 over r2. That's how the relationship works, okay, etc. I mean, you can increase it any way you like. All right, that's just the technology that goes with a record. On a compact disk, V has to be constant or preferable, let's say, or let's say there's no reason to change the speed V because you want to record the data at a certain rate. But as a result, omega has to change now. If V is constant, R, let's say, goes down, so omega has to compensate for that, all right? So if R goes down, omega has to go up. So you would expect the compact disk to spin faster and faster as the laser reader comes close to the center. Okay. Now, when omega changes, which means the object is spinning up, let's say, spinning faster and faster, this means even without changing your position on the rigid body, your V has to increase as well, all right? Now, for Earth rotates around its axis, which goes through the geographical north and south poles, all right? So here's North Pole and South Pole, okay? And then rotation is, let's say, like this. How do I know which way Earth rotates? Well, I'm thinking about the fact that the sun rises from east, right? So if I place the sun over here, okay, and here we are in North America, and here's South America, right? So here we're in Houston, let's say. The sun has to rise everywhere on the Earth. The sun has to rise from the east direction. So it has to spin this way. All right, so from west to east. Anyway, so if that happens, of course, omega is pointing along this axis. Is omega changing? No. A day is 24 hours, right? That doesn't change. So there is no alpha here. Alpha is 0. Now, omega is a constant. What about V then? Well, V depends on where you are. On a sphere, you know, there are parallels, right? These lines called parallels that are perpendicular to the greatest of these is the equator line, right? Then you have circles getting smaller and smaller, and a point at the poles, right? So we're not at the equator, but we're still at a certain distance from the rotation axis, this axis here. Okay, therefore, we do have a tangential velocity. But somebody in Canada, let's say, somebody in Canada over here, now that will be closer to the rotation axis, a different r, smaller r. Therefore, the rotational speed is the same, but the tangential velocity will be less. All right, and on the North Pole, you'd be just completing your rotation in 24 hours with 0 V. All right, so that's the most important relation then in this slide here. V is equal to omega times r. And for a rigid body, v depends on where you are on that rigid body. So v is measured in meters per seconds. Omega is measured in radians per seconds. And of course, r in meters. So radians per seconds times meters is, again, meters per seconds. Radians is just dimensionless, okay? The dimension wise, v has a dimension of length over time, but omega has the dimensions of 1 over t. All right, so radians per second is the unit, or RPM, revolutions per minute, very common units for both circular and rotational motion. Now, what about alpha? Now, I said for Earth, there's no alpha, okay? But what about a spinning top? You know, its omega will change. There's friction and all that. A spinning top, like this, spinning about an axis here. Okay, now omega will change, therefore there will be alpha. If there is alpha, we know that a point you pick on the top will also have a tangential acceleration, A10. Now for rotational motion, let's not worry too much about the radial acceleration. Of course it's there, but it won't really help us, okay, to analyze the rotational motion. But this point here, let's just focus on the tangential acceleration for a moment, which is a vector, of course. Now, how is that related to alpha? What's the relation between this and the angular acceleration vector alpha? Okay, so this relation here will help us understand what's going on here. Now, the tangential acceleration tells us how v changes in time, right? Now, for this point here, if v changes, we're talking about delta v over there. Now, on the right-hand side, we have omega and r. But remember, r is fixed. We're talking about a particular point on the spinning top. So r doesn't really change. R is just a constant there. What changes is omega. All right, so omega changes in time, so does delta t. Now, I want to erase the vector signs on the symbols here. There's a reason for that, but let me just erase them for now. Okay, I'm thinking about just the magnitudes. So, and you can do it for a very infinitesimal change in time, for a very short time interval as well. So here's what you get. Alpha, oops, go back to the pen here. Alpha, the angular acceleration, will be multiplied by r to get the linear or tangential acceleration. Okay, greater the distance from the rotation axis, greater the tangential acceleration. So these two formulas are really symmetrical, these two. So tangential acceleration is in meters per second square, radius is in meters, and alpha is in radians per second square. Okay, so again, alpha has the units, I'm sorry, dimensions of 1 over t squared. All right. Good. So these two, okay, please remember these two relationships between the rotational and linear quantities. These are important. Now, going back to the vector nature of omega v and alpha and a. In the previous slide, I mentioned theta and s, right? Let's remember those. I think it went something like S was equal to theta times theta cross R. Double check that. But now we have a similar relationship for V and omega. So omega times R should give you V. All right, so what if I have A here, alpha cross R. So that's the vector nature here of these variables and how they are related. And since the vector product has a magnitude, okay, let's remember any vectors when multiplied in this fashion, the magnitude of the vector product will be equal to A magnitude times B magnitude times the sine of the angle between the two vectors. That's the general relationship. In our case, these three vectors are perpendicular to each other, so the angle is 90 degrees. Okay, so this is sine 90 for these, which means 1. Okay, so that explains why we have the relationships on the left in the boxes. Okay, there is no sine theta. I mean, theta is 90 degrees there. Okay, so that is about the units, dimensions, and the vector product. Now, in some books, you may have the vector products in a different order. That could be a convention. I need to double check that, but don't worry about that too much for now. Okay, like omega cross R gives you V. Okay, what if it is R cross omega? So R cross omega. It's something I have to check later, which is not too important right now, okay? All right, so next thing I want to talk about is the kinematics of this. And this was also covered in circular motion. Let's just go over it for rotational motion. And we're gonna be focusing on cases when alpha is a constant. Okay, alpha is a constant in magnitude and also in direction. Do we see such examples, you know? Well, it could be. I mean, you could approximate alpha to a constant, you know. If you're, let's say you have a fast car, sports car, you know, you want to reach to 100 miles per hour in that many seconds, okay? So hit the accelerator, okay? Well, maybe it's different when you drive a stick shift versus an automatic transmission. But for practical purposes here, for this class today, let's assume that the speeding up of the wheel is uniformly accelerating. So let this be omega in radians per seconds. This is just one wheel. in time. It speeds up. And then once you reach 100 miles per hour, you maintain your speed for a while. And then there's a stop sign over there. You got to slow down, hit the brakes, and omega decreases linearly again, something like this. Now, I'm not claiming that in real life when you're driving your Toyota, okay, you have this exact picture. I'm not saying that. Even omega during the speeding up and slowing down phases, it may not be a straight line, but assume it is, all right? Assume that it is. Then these slopes here, constant here in the first phase. It's this slope. In the second phase, it's just a flat horizontal line. And here you have this slope here, okay? So you have 3 phases, 1, 2, 3. Now, there's not one formula that fits everything here. So you got to divide it into phases, because in each phase, alpha remains a constant, all right? Now, when you're speeding up, okay, here's the car and its wheel. So here's the wheel. Okay, here's the car. I'm trying to draw it in 3D. So here's your car. Okay, so the motion of the car is this way. So while the car is moving this way, that's your linear speed, right, for the car. A point you pick on the rim will have linear speed in that direction, where this is r and etc. But the angular speed can be found using the right-hand rule, remember, which would give you a direction perpendicular to this. That's the direction of omega as the car moves in that direction. What about alpha? Well, that depends whether you're in phase 1 or phase 3. Of course, in phase 2, there's no alpha, or it's the constant 0, okay? The slope is 0. But in the first part, you have a positive alpha. Here, you have a negative alpha, which means that if you take the direction of omega as your positive direction, this is the positive x direction, let's say. Well, no, it doesn't matter what you call it, x, y, or z, doesn't matter. But in that direction, if alpha is positive, this means alpha is pointing that way. Also, this is the direction of alpha. Okay, when speeding up, speed up, first phase. If you're in the third phase, okay, let's use a rainbow pen. Let's use a rainbow pen in the opposite direction. This alpha is for slowing down, phase 3. Okay, so that's what I mean by constant alpha. It's an approximation with these slopes are constant, and the direction within that phase is also a constant. So alpha is a constant. So if that happens, we have formulas that will relate theta, the position variable, and delta theta, which is the displacement variable. So that's delta theta, which is defined as theta final minus theta initial. We're going to relate this now to angular velocity and acceleration. Now, the first formula is omega initial times t plus 1/2 alpha t squared. Now, we should recognize this form right away from the linear equation. You know, if you simply replace delta x with delta theta, and V with omega, and A with alpha. This is what you get. So alternatively, if you don't know what alpha is, but only know the initial and final angular velocities, just take the average of the two and multiply by t. Okay, and the final angular velocity in that phase is given by omega initial plus alpha times t. And if you don't know the time, you can still work with these variables. Omega final squared is equal to omega initial squared plus 2 alpha delta theta. Okay, so I'm not going to spend too much time on the derivations of these because we've done this for linear motion. I'm just replacing the variables with the rotational counterparts. And also I went over these when I did circular motion. Those are the kinematics equations. Kinematics when alpha is constant. If you want, you can add a fifth equation. What if you want to write, let's say, delta theta in terms of the final angular, it's not very common, but possible, final angular velocity. So omega final times t. Okay, you just take this equation and plug it in here, and then you get negative or minus 1/2 alpha t squared. Okay, so that's, you can call that fifth equation. All right, and if you want, you can write these as vectors if you really want to do that. Okay, let me just add it. So remember, these were vectors, right? So delta theta as a vector will be equal to t times omega plus 1/2 t squared times alpha, etc. Okay. Now, what makes this different from circular motion is, now we have not just a point on the rim of the tire, but we have the whole wheel. Okay, the whole wheel. So a point R1 away from the center, and another point R2 away from the center. These share the same omega and therefore same alpha, but the linear speeds will be different. Now, let's say we want to find energy associated with this motion. Okay. Now, if you want to do that, the energy of a rotating wheel. Okay. Now, for a car, okay, we have to take into account a couple of things. First of all, these points M1 and M2, and then there are a million of those. They are not just rotating about the axis of the wheel, but the car itself is moving. Okay. So there are two types of motion here, rotational and translational. And if the object will have some energy, and kinetic energy I'm talking about, I will need to take into account the contributions from both. Okay. For now, let's just focus on the rotational part of it. Okay. So what is the kinetic energy of the Earth? You know, as a globe, as it rotates, what will be the kinetic energy? The kinetic energy of a rotating solid object. Whether it's speeding up or slowing down, doesn't matter, because we're looking at the kinetic energy at an instant anyways, okay? Kinetic energy. Now, the only kinetic energy you know so far is the one we did in class, 1/2 mv squared. That's the kinetic energy. We define it like this, okay? The definition of kinetic energy. This mass, though, what is it for a rotating body? That's the question now. This works for a point particle, yes, or for an object, okay, which is not necessarily a point, but you throw it, or a ball, you know, you may assume that all of the mass is concentrated on one point, which you can call the center of mass. You know, as it flies, it's going to have a speed, instantaneous velocity, and square it and multiply that times the concentrated mass divided by 2 kinetic energy. But this is what we were ignoring, okay? The rotation of the object as it flies, that has to contribute to the kinetic energy as well. So going back to this example of a spinning top or spinning globe, the points that make the globe, each little tiny particle, they don't move with the same speed. We already saw that, right? The speed that they have will depend on how far they're from the center. So just imagine a little cube here with mass m that is r away from the center, not center, the axis of rotation. I'm not talking about the center of the object. I'm talking about the distance from the rotation axis. And it's going to have a velocity in this direction, perpendicular to the radius. Fine. That is v. But I know that if I pick another one here, over here. Now this is my r, and this is my v. Much less. I'll call it r prime and v prime if you like. A different one. And there are a million of those. So why don't I actually use indices? How about that? Let me call this ri, and call this one mi. You know, those little cubes don't have to be the same size. Anyway, so we have this index that goes from 1 to a really large number, n. All right? And the total mass of the object, let me use capital M, will be the sum of these little masses, m1 plus m2, dot, 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 all the way up to mn, or if you want to use the fancy notation, sigma I from 1 to n, mi. And each mass will have a different radii from the rotation axis, which are denoted by Ri. Okay, so do you see now what I mean by which mass that is going to go into the formula, kinetic energy? Obviously, I cannot just use the capital mass there because that corresponds to many different velocities there. So here's what I do. What is the kinetic energy of this little cube there? Let's start there, that little mass mi. I'm going to call it kinetic energy of the ith particle. Now that is easy. Use the same formula, 1/2 mi times vi squared, okay? I mean, smaller the particle you pick, the better. It's a good result. But when the object rotates as a whole, you have thousands of these rotating about that axis. So I need to add them up. You know, the kinetic energy of the object, the globe, is nothing but the sum of those little contributions to the kinetic energy. So the total kinetic energy should be a sum of the the individual parts. So if you add them up, what happens? Okay, so 1/2, and then I'm adding over summation over mi and the corresponding velocity squared. All right, there is no r there yet. Let's put r there. How do we do that? We remember the relationship between omega and r. Omega is a constant for all of the particles. And that is vi over RI from the previous slide, okay? V is omega R, therefore omega is V over R, or VI is equal to omega times RI. I'm going to take this and plug it in here. Now, V squared means omega squared RI squared. Omega is a constant. I can just write it over here outside the integral. Not integral, sorry, the summation. It works for integrals too. So 1/2 times this summation here, which will have only mi, and inside v there is r, so ri squared. And then when I'm done adding those, I will multiply this with omega squared, which comes from v squared. So omega squared. But omega is the same for all points on the object. So I'm not doing any summation over omega. So this thing in the parentheses, I'm going to give it a new name. I'm going to call this rotational inertia. That's one name, rotational inertia. You're familiar with the term inertia from linear motion, or alternatively, moment of inertia. Okay, both are used. Either rotational inertia, moment of inertia, and the letter I. Okay, now this is where you have to be careful. The letter I stands for rotational inertia. Where did we use I before? Do you remember? I. But this I was not a scalar here. Okay. Note, not to be confused with this I, which was impulse. Now, some books, in order to avoid that confusion, use the letter J, which is fine, or J to show impulse, but most people would call it just I because of impulse, right? But that is a vector, okay? This is a vector. This sum is just a scalar. Two different things, okay? There are only that many letters, but too many concepts in physics, so we're gonna use the same letter for different concepts. Same as T, capital T. Capital T is period. The time required to complete one cycle, which is related to omega actually, 2 pi over T, right? This comes from, well, you can think of it like a circumference. Remember, it was 2 pi r. So if you multiply this by r, you'll get v. That's period. But we used T before for tension, force in a cable, right? Totally different idea, different concept. So if you look at a formula sheet, the formula sheet will not have the descriptions of the variables. It will just have the formulas. So if you take the formula for impulse and apply it to rotational inertia, you're done, okay? You're done meaning you get F, all right? So please be careful. This is only a scalar called rotational inertia, or moment of inertia. Has nothing to do with impulse. This is a scalar. So now we have a kinetic energy formula for a spinning top, or for any object, any rigid body for that matter. If you know how to do that summation, just write the kinetic energy now as 1/2 I omega squared. See, it just looks like the original form. So m is replaced with I. and V replaced with omega. 1/2 I omega squared is the formula for the kinetic energy of a rotating body. If the rotating body also moves, translates, you have to add that to the game as well. So the total energy will be 1/2 mv squared plus 1/2 I omega squared, the translational and the kinetic parts. So in general, total kinetic energy will be from translational and then rotational parts. This is translational, this is rotational kinetic energy. But you still have to find out what I is, what moment of inertia is. You got to know how these masses are distributed. You know, now, there are simple ones where the mass is distributed uniformly. Okay, a compact disc, for instance, made of that material, plastic, whatever, or vinyl record. It's the distribution is smooth. In other words, the density, mass density, is a constant. It does not depend on the position, for instance. But there may be objects, you know, alloys or composite materials, you know. As you move along the object, you know, there's maybe lead and then gold and aluminum used, you know, it's a mixture. So density changes as R changes, you know. So those problems will be a little more difficult, you know, because you got to know the mass distribution, how it is exactly, so that you could calculate the moment of inertia based on that. All right. So let me go over a couple of really simple cases and see how we can calculate the moment of inertia. All right. So I'm out of space here. Let me just erase everything here, clear canvas. And let's start with the very simple cases. The simplest you can imagine is, of course, just this point here, cube, and the axis, rotation axis is there. It's R away. So this object is in a circular path. Yes, the kinetic energy, if you write it as 1/2 I omega squared. If the mass is m here, I has to be simply mass times r squared. Because if you multiply it by omega squared, you use the fact that, you know, r times omega is v, so you get 1/2 mv squared. Okay, so for just a point particle going in circles, let's change the direction of rotation and put v here now. It's really simple. Okay, I mean, you don't even need to do rotational ideas or moment of or anything complex to understand what the kinetic energy here is. But the moment of inertia turns out to be just mr squared. All right, now what if I add more masses into the picture, but they're all are away from the center? Okay, add one more piece, another one, another one, another one, another one. Like beads, you know, lined up. You take a ring, you know, a very light ring, mass negligible, but that ring will carry those beads. Each will have a mass, okay, m1, m2, etc. But the thing is, they're all are away from the rotation axis. And if I glue those beads together, it becomes a rigid body, but it's still rotating, okay? So what we end up having is what you call a hoop. A hoop. Okay, a hoop is a ring with a mass distribution. Okay, I don't like the way that this one looks. Okay, let's say that's the hoop here. Now in the beads case, of course, you can fit only a number of beads there. Let's say 100 beads around the ring. So I will be then, for this specific case, I will be, well, you add them up. M1 times R1 squared plus M2 times R2 squared, M100 R100 squared. Okay, you simply add the masses. What if there are too many of those? It's a continuous distribution. Okay, it's a uniform, like an actual ring. Okay, what happens then? Now R1, R2, R100, these are all equal to R. So even for the bead example, you end up with M1 plus M2 times M100 times the common R squared. If it's a continuous distribution, not a collection of point particles, beads, then you take it as the total mass, M. Total mass is equal to M. So M times R squared, and you're done, okay? This will be the moment of inertia of a hoop, all right? Of a hoop. Now, what if it's a compact disk? What if now there's mass inside? All right, so these little particles are at different distances. Okay, this is a solid disk. Now, how do you find the moment of inertia for this? Because you can factor R out like you did before. What will be the moment of inertia? Now, this I cannot explain without calculus, all right? Meaning I cannot derive the formula for moment of inertia for a solid disk without using calculus. So I'm going to make a separate video for university physics students who need to learn how to calculate this. But for college physics students, just take it as a formula, okay? You have a table in your book. Different objects, disk, sphere, cylinder, okay? What you will see in that table is there will be a constant, a fraction, a number, a scalar in front of this mr squared. So the total mass is still m, and the radius from the radius of the object is, let's say, r. Okay, so you will have here the mr squared, but you're going to multiply it by a factor, which happens to be 1/2 for the disk, solid disk. All right. So you may have a combination of the two. So you may have actually a CD indeed looks like this. There's a hole in the middle, right? So same thing for the record. So you have two radii, inner and outer radii. Okay, so for this object, the mass is only here, a donut shape, maybe you can call it, you know. But it's flat. It's a disk with a hole in it. Now, the moment of inertia, if the total mass is m, again, just take it as a formula. I'm going to show you how to derive this in a separate video. Is this, okay? And let's say you take that solid disk and then add mass here. This is your solid disk. Now you add mass along the direction of rotation here, and you make a cylinder out of it. Actually, every object that we have, which looks like a disk, is actually has a very small thickness. It's a cylinder. In real life, there is no two-dimensional real-life objects, right? So anyways, this has now a depth. Let's call it L, all right? And the rotation axis is here. See, these I's, the moment of inertias, are always with respect to an axis that goes through the object. You know, if I don't tell you where the axis is, you cannot tell me which I to use. For these simple cases, I's are in the center, meaning the axes are in the sample and in the center. And I'm going to show you a way how to find it if it's off center, okay? If it's a cylinder, all this mass you add below or in the direction of that axis, they don't really contribute to the form of the function here, but they do contribute to total mass. So it's still, it's a solid cylinder, let's say, solid cylinder. Use that same form, 1/2 mr squared. Just keep in mind, m is the total mass and r is the radius. So you can take this idea, apply it to this, you know, with the mid portion removed, or even the hoop. If it is a hollow sphere, not sphere, hollow cylinder, hollow cylinder, I is just mr squared. Okay, you can take a paper, just take a paper and then do this. Okay, if you rotate it about the center in the middle, the moment of inertia is just mr squared. Okay, so that's for a cylinder. And if you look at that table in the book, you will have a sphere. Okay, let me just include it here. So solid sphere, 2/3 mr squared, hollow sphere. Okay, I think one is 2/5, one is 2/3. I'm going to check those in a second. Give me a hollow sphere, mr squared. I'm not supposed to forget these, but I just did. So, so we're talking about 2/3 and 2/5. What was it? Rotation. So uniform sphere, 2/5. That will be solid. So solid sphere. Let me double check. Two-fifths. Again, I'm going to show you how to calculate this in a separate video using calculus. All right, 2/5 mr squared. And hollow sphere, did I say 2/3? Okay. Let me not embarrass myself and then find it from the book. 2/3. Yes, thin-walled hollow sphere, 2/3. Solid sphere, 2/5. Okay, and a table like this in your book. Okay, so just go through the table. There is a rod, a rectangular plate, and all. So this is how you find the moment of inertia. And what if the axis does not go through the center? Again, without proof, let me also mention that. And that is called the parallel axis theorem. So suppose an arbitrary shape which has a center of mass, I don't know, here, I guess. This is the center of mass, and there's an axis that goes through the center of mass. It's spinning like this, okay? Now this will have a moment of inertia, I center of mass, all right? Let's use numbers. Let's say this is given to you, 5.2, okay? It's gonna have the units of, well, whether it's mr squared, so kilograms meter squared. Well, you wanna find the moment of inertia with respect to here, this axis that goes through, you know, a different point here. And all you know is the distance between the two. Call it D. All right, D is given. D is 2 centimeters, let's say. And this is 0.1. So what is I1? All right, how would you find that? And why would you need it? Well, not all rotating rigid bodies are rotating about an axis that goes to the center of mass. I mean, there are mechanical parts in your wristwatch. There are so many parts that are rotating, you know. So, or maybe a clock, a grandfather clock has a pendulum that looks like this. A rod and then a piece here, and maybe a screw, okay? And it's about to rotate about an axis here. And you wanna set up the clock, so you wanna set the time, you use that screw and then change the position of this mass here, which is L away from the center, etc. So you may have many cases where you'll need objects which are not pinned at their center of mass. The door, right? When you open the door, you enter a room. Here's a room with a door. And the door is hinged. No, I didn't want that. The door is hinged here. Here's the handle. You want to open the door. It's a rotation, right? It's a rotation like this. But the rotation is not about an axis that goes through the center of mass. The center of mass would be here. Maybe it's somewhere in the, or an axis that goes to the center of mass, let's say, will be here, you know? No, it's not the case here. So how do you find the new moment of inertia? You use what is called as a parallel axis theorem. The parallel axis theorem. The proof is not difficult, but I'm going to write it without the proof here. You just write the center of mass moment of inertia and then add to it the mass of the object times d squared. So in this case, it becomes 5.2 kilograms meter squared plus, okay, let's say mass is 1 kilogram. Plus 1 kilogram times 2 centimeters, which is 0.02 meters squared, okay? So this will be obviously greater than 5.2. Anytime you move to the edge of the object, you're increasing the moment of inertia, all right? And maybe if you're using baton, you know, and then you rotate it like this, you can feel it. Like you try this versus that, okay? And it feels different, right? I'm going to talk more about what that difference corresponds to in terms of dynamics, but let's not go there. Let's not think about in terms of force or anything like that. It just feels different. That difference, that's the thing you feel, is because of that, okay? This change in the moment of inertia. So the moment of inertia is the minimum when you're at the center of mass. If the rotation axis is close to edges, it increases. And that's called parallel axis theorem. And you can use it, let me give you another example, to find interesting things. Let's say, okay, the object is a rod like this, or some, I don't know, arbitrary object. This could be, chopsticks, okay? And somebody tells you that they measured the moment of inertia about this axis here. And that is equal to 3 kilogram. Okay, for a chopstick, that's a huge number, so it's something else, okay? A steel rod, let's say. And you're supposed to find the moment of inertia with respect to this axis. This is I1. You're supposed to find I2. Okay, let's say the first one was 0.7 meters from one side, and this guy is 0.3 meters from the other side. And how are you going to find I2, right? Using the parallel axis theorem. Because you know that this object here, at the center of mass, if it's a uniform steel rod, it's going to be the center. Doesn't matter where it is, really. Well, actually, it does matter in our case, because we need D, right? So if somebody tells you that the total length of the rod is, 3 meters. The total length is 3 meters, okay? This is given, and you're supposed to find I2. You have the dimensions, you know that the two axes are parallel, and the total length and how far from each side. You can still find I2 by applying the parallel axis theorem. You just need to remember that the center of mass will be at the center. So from one end to the center of mass is only, 1.5 meters, right? So the two D's, D1, and let's call it D1 and D2. Okay, so this is 1.5 minus 0.7 meters, and this is 1.5 minus 0.3 meters. All right, so we know all the dimensions now, 0.8 and 1.2 meters. So I know that from parallel axis theorem, I1 has to be equal to ICM plus mass of the rod, D1 plus D1 squared. And also I2 has to be equal to ICM plus MD2 squared. Okay. Now M is not given. Maybe we should know what M is. But the point is, you can eliminate the thing that you don't need, which is ICM, right? So if you subtract I2 from I1, let's say, I1 minus I2 will be equal to M D1 squared minus D2 squared. So if M is given, yes, if M is given, you can find, actually, you can find M. You can find M. It doesn't have to be given to you. Let me show you how. Remember the table in the book? This table? In the table, there's a formula for I center of mass. Okay? That is 1 over 12. 1 over 12 m radius squared. In this case, it is L over 2. No, it's L. I'm sorry, it's L. 1 over 12 m L squared. L squared. Okay, so you could plug it in here and solve for m, and then use that m in the second here equation to solve for I2. So let's do it. So I1 will be equal to ICM, which is m times 1 over 12 times L squared, 3 squared, plus m times, m is factored out, D1 squared, and D1 was what, 0.8? 0.8 squared. Okay, so I1 is equal to 3. We have that. Let me just write 3 here. 3 kilograms. I'm not writing units, just writing the actual value, 3. So we can now calculate m from here, right? So this will be 9 over 12 plus 0.8 squared. That's my calculator. So 9 over 12 plus 0.8 squared, 1.39. 1.39. Therefore, m is 3 divided by 1.39. That is 2.16 kilograms. And take this m and plug it in here now to solve for I2. Therefore, I2 will be equal to I1 minus this, which is I1 is 3 minus m 2.16 times D1 squared minus D2 squared. D1 squared is 0.8 squared minus D2 squared, that's 1.2 squared. Okay, so 3 minus 2.16 times 0.8 squared minus 1.2 squared. I got 4.728. You see what's happening here? It's increasing. If I did it correctly, 728 kilogram meter squared. It was 3, but that was when you were 0.7 meters away from one end. Now you're getting closer to the other end. You know, you move 0.4 meters. Now you're only 0.3 meters away from that corner. Okay, effectively, you're moving away from the center of mass, so the moment of inertia goes up. All right, so that's another application of parallel axis theorem. So as an exercise, go through that table in the book. Take a cylinder, for instance, of a given, size m and r. You know the moment of inertia, that's 1/2 mr squared. If the 1/2 mr squared, if the axis goes to the center. Now calculate the new moment of inertia with respect to this axis. Okay, as an exercise. All right, I'm going to stop this video here. And in the next video, I'm going to show you how to calculate the moment of inertia for given mass distributions using calculus. So if you are a college physics student, don't worry about that video. But if you're in university physics, please watch that video. Okay, let me stop now.